Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable and ready to wander with me into the strange distant quiet of the Oort Cloud. A realm so remote that sunlight itself arrives only as an idea more than a force. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. As the narration settles into its slow rhythm, the journey begins with a steady outward drift through the solar system's thinning light, moving beyond the familiar planets and the scattered worlds that orbit far from the sun's warmth. The space between objects stretches wider until each body becomes only a faint punctuation in an ocean of dark, and the sun shrinks until it resembles a pale star suspended in a black expanse. Out here, influence blurs into suggestion, light weakens into memory. Beyond the orbits of Neptune and the long elliptical path of Pluto, beyond even the drifting population of the Kuiper Belt, the last structured region of the solar system begins to dissolve into an almost perfect stillness. Only took a few billion years for the boundary to become this quiet. The narrator moves through a region where the sun's gravity continues to act, though, with a faintness that feels more like a whisper than a pull, and the pressure of the solar wind no longer shapes the space around it with any clarity. With each passing astronomical unit, the familiar patterns of planetary motion fall behind, leaving a realm unvisited, unlit, and unhurried. Only took the galaxy's slow rotation to spread these distances so far apart. In this dim frontier, scientists infer the beginning of the Oort Cloud not through observation, because no telescope has ever seen it directly, but through the long looping paths of rare comets that return from orbits so extended they vanish into numerical abstractions. A single comet traced backward through centuries of quiet calculations hints at a spherical reservoir surrounding the solar system, a halo of icy bodies scattered across distances so wide that Earth's entire orbit would fit into them tens of thousands of times. Only took a few million years for a comet to complete one such orbit, drifting at speeds so slow that ice sublimates only when it enters the inner solar system, leaving the rest of its long journey in unbroken darkness. The poetic detail out here is the colour of the darkness itself, not black, but a deep metallic grey, shaped by the absence of nearby stars, a shade produced by sheer emptiness rather than shadow. It is the kind of darkness that feels ancient, as though it has held its shape since the sun first lit its nuclear fire. Within this dimness, the particles that do exist, dust grains older than Earth, ice crystals that predate the moon, fragments of primordial material, untouched since the solar system's youth floats silently. At these temperatures colder than anything naturally occurring on Earth, molecular motion slows to nearly nothing. Water becomes a solid so hard it behaves like stone. Carbon monoxide freezes into fragile matrices. Hydrogen, usually restless, condenses only in fleeting patches. These conditions preserve objects across unimaginable spans, allowing a cometary fragment to remain unaltered for billions of years, a frozen time capsule drifting so slowly it experiences almost no change at all. The scientific fact grounding this region is simple. The Oort Cloud is the most distant part of the solar system, extending perhaps tens of thousands of times farther from the sun than the Earth does, and it is shaped into a roughly spherical distribution by the combined influence of the sun's gravity and the gentle but persistent nudges from passing stars and the galactic tide. Yet even here a quiet scientific mystery remains. No one has ever directly observed the Oort Cloud. All knowledge of it emerges from inference orbit modelling and the behaviour of long-period comets that appear with periods so immense they feel almost like interruptions from a forgotten era. The sun glows faintly behind the narrator as a tiny star, only one among many, offering neither warmth nor direction beyond a small dot of memory. Like a lantern glimpsed from a mountaintop, it becomes a reference point rather than a presence. Only took the thinning of light to make the sun feel like one star among countless others. The great distances here create ironies folded softly into the structure of the solar system, a region dominated by the sun yet barely affected by its radiance. A cloud shaped by gravity yet drifting too loosely to be seen. A boundary that exists precisely because it cannot be defined sharply. As the narrative drifts farther outward, the faint pull of the sun weakens so gradually that it never provides a precise moment of departure, only a sense of transition. Like walking from shallow water into deeper ocean, the shift is continuous, offering no clear edge where the solar system ends and interstellar space begins, and so the narrator lingers in this twilight of influence, where the Oort Cloud is thought to arise from the accumulation of ancient bodies, icy relics cast outward during the solar system's formation, now resting in orbits shaped more by galactic tides than by solar authority. It is an environment built not on activity but on persistence, a place where time stretches so broadly that processes hardly seem to occur at all. Only took the universe's patience to allow such stillness to form. The scene settles into a muted stasis, the narrator suspended in a silence so complete, it feels older than the planets, older than the sun, older even than the clouds of gas that once coalesced into the earlier stars. Out here at the threshold of the Oort Cloud, the solar system's story shifts from the active illuminated physics of planetary formation to the dormant frozen endurance of an ancient scattered sphere. And in this quiet, the narrative prepares to move deeper into that sleeping army of cometary bodies, where age, cold, and distance combine into one of the most tranquil expanses the universe can offer. The narration drifts deeper into the faint outskirts where dust older than oceans moves through a darkness that barely changes across billions of years, the kind of darkness that holds its shape, not because anything surrounds it, but because almost nothing has ever disturbed it. Dust grains out here originate from the earliest moments of the solar system's birth, tiny fragments forged within the collapse of the sun's primordial nebula, long before Earth cooled, before its crust formed, before liquid water pooled into the first ancient seas. These grains carry isotopic signatures that hint at environments far older than any rock on Earth, tiny records of conditions from a time when the solar system was still a swirling disk of gas and ice. Only took a few million years for those earliest particles to form, though the span feels trivial compared to the 4 billion years they have floated since. As the narrator moves through this region, the dust becomes a faint presence rather than a visual feature. It is too sparse to reflect sunlight and too cold to glow, yet it exists in vast numbers, each grain travelling along its own orbit, shifting imperceptibly with the slow pull of the sun and the even slower tug of distant stars. Each particle is a survivor of the solar system's violent youth, when collisions, mergers, and gravitational scatterings filled space with chaotic motion. Only took the solar system's early turbulence to fling this material outward, sending uncounted fragments into trajectories that stretched farther than any planet's reach. In this still exterior, the narrator visualizes a grain of silicate dust from the earliest nebula era, shaped by freezing temperatures into crystalline forms that would shatter instantly if warmed beyond the extreme cold of this environment. Some grains contain tiny inclusions of pre-solar material remnants of stars that lived and died long before the sun ignited. These inclusions offer a gentle cosmic irony, while planets formed from mixed and melted elements, the most unaltered samples of the galaxy's past now float in a place so remote that no sunlight touches them directly. Only took the universe's patience to store such ancient relics in the loneliest part of the solar system. The scientific fact guiding this region is the survival of primordial dust in the outermost solar halo, preserved due to the absence of thermal and chemical alteration. In the inner solar system, such grains would have been melted, incorporated into larger bodies, or transformed by planetary processes. But out here, temperatures hover only a few degrees above absolute zero, slowing all chemical reactions to a near standstill. Ice becomes rigid as minerals and carbon-rich compounds persist unchanged, across epochs, measured not in millions but in billions of years. The lesser-known detail rests in the isotopic compositions of some dust grains that ultimately reach Earth. They contain oxygen and carbon ratios that do not match the Sun's own chemistry, implying origins in nearby stars that seeded the young nebula with ejecta. This material travelled enormous distances before joining the solar system's earliest building blocks, and some of it now lingers in the Oort Cloud, preserved in near-perfect condition. These grains hold memories from eras far beyond the solar system's birth, their journey a silent testimony to stellar life cycles sculpting cosmic environments across time. Yet a quiet uncertainty remains. Scientists do not fully understand how much primordial dust still exists in the Oort Cloud, or how it is distributed. Its presence is inferred through models, cometary samples, and interplanetary dust collections, but direct measurement is impossible without visiting these farthest reaches. The distribution of dust might be clumpy, or nearly uniform, sparse, or unexpectedly dense. Only future missions, still technologically distant, could reveal its true structure. Out here, movement itself becomes slow, and ironies settle gently into the dim environment. Dust older than Earth drifts through space that Earth will never reach. Fragments from exploding stars rest in the calmest region of the solar system. Materials untouched for billions of years continue to move in paths shaped by distant galactic forces. Only took the galaxy's long rotation to scatter such relics into positions so remote that even starlight is hardly a presence. The narrator imagines a dust grain's perspective not as a character, but as a physical state remaining frozen in orientation for spans so long that the Milky Way itself changes shape slowly around it. Like a leaf drifting in an ocean where currents shift over millennia, it maintains an orbit gradually distorted by the soft tides of the galaxy's gravitational field. The analogy becomes a gentle breath of modern reference. These grains drift like forgotten seeds, carried by a wind too faint to feel. The sun's influence persists, though only as a distant gravitational echo. At tens of thousands of astronomical units, its pull becomes weaker than the combined effect of passing stars and molecular clouds drifting through the galaxy. Yet even these outside forces act slowly. A star moving within a light year of the Sun might adjust the orbits of Oort Cloud objects over millions of years, nudging a few inward while leaving most untouched. Only took the slow dance of distant suns to shape the cloud's broad geometry, a reminder that the solar system is never fully isolated from its galactic environment. The dust here holds another poetic detail. Because sunlight is so weak the grains do not shine, yet they scatter starlight faintly in wavelengths too subtle for human eyes to perceive. Instruments tuned to long infrared wavelengths might someday detect this dim glow, a radiance produced not by heat, but by the mere fact of existence in the coldest conditions. This glow, if observed, could reveal the structure of the outer cloud, but for now it remains hidden, a soft scientific mystery waiting in the dark. As the narrator continues outward, the dust becomes even more diluted, though still present, spread across volumes so vast that the distance between grains could rival the distance between small asteroids near Earth. Each one moves independently, obeying orbital mechanics that unfold so slowly that their motions seem like stillness. Only took the vastness of interplanetary distance to make motion indistinguishable from rest. In this domain, dust older than Earth's first ocean drifts without urgency, a suspended archive of material from before continents rose, before life emerged, before Earth even existed. These grains are the quiet witnesses of cosmic beginnings, their surfaces unmarked by weather, wind, or light. And in this expansive silence, the narrator drifts onward deeper into the Oort Cloud's sleeping reservoir, where the icy bodies that orbit here carry even larger and older secrets than the dust that surrounds them. The narration drifts farther outward into a realm where the dust thins into near nothingness, and larger fragments begin to define the architecture of this frozen frontier. Here, the slow freeze of cometary shells becomes the quiet focus, a process that began long before Earth ever cooled enough to host its earliest rainstorms. These bodies, some as small as mountain boulders, others stretching many kilometers across, hold within them the volatile ingredients that once shaped the young solar system. Their surfaces are so cold that even nitrogen and carbon dioxide, which evaporate easily closer to the sun, remain locked in rigid crystalline layers. Only took the ambient temperature of deep space to preserve these compounds in a state unchanged for billions of years. As the narrator glides through the dark, each cometary body appears not as a gleaming orb but as a shadow, against an even deeper shadow, its presence revealed only by the faintest scattering of distant starlight across its uneven geometry. The scientific fact grounding this space is clear temperatures in the outer Oort Cloud fall to only a few degrees above absolute zero cold, enough that molecular motion slows, almost to stillness, allowing amorphous ices to form structures that lack the organised crystalline patterns familiar on Earth. These amorphous ices can trap gases within their matrix, creating mineral-like cavities where volatile molecules remain bound until warmed dramatically during a rare inward journey. The gentle irony is that these ices, fragile under any terrestrial condition, become durable only in this extreme cold. A comet that would crumble instantly near a warm star remains intact across the slow geometry of galactic time. Only took cosmic cold to make fragile materials strong. Some comets exhibit layers formed by repeated freeze-thaw cycles during occasional mild heating events, not from sunlight, but likely from distant stellar encounters, or passing molecular clouds that shifted their orbits slightly. These events are so rare that a single cycle could require millions of years, which folds another subtle irony into this quiet region. The most dramatic changes in a comet's structure may have occurred before multicellular life even appeared on Earth, leaving its present form essentially unchanged since those ancient disturbances. Only took a passing star to sculpt a comet's face in an era long before Earth's first forests. A poetic detail emerges from the way these ices reflect heat. Although invisible to the eye, they re-radiate faint infrared energy from the distant galaxy, creating subtle thermal gradients across their surfaces. These gradients are whisper-thin, only a fraction of a degree, but they can across millions of years gently shift a comet's rotation, or alter the distribution of trapped gases. This thermal dance, so minor that it would be undetectable on human timescales, becomes meaningful when the timescale stretches into geological breadths. A comet might rotate once every few days, but its orientation could drift by a fraction of a degree each millennium, eventually creating entirely new surface patterns sculpted by the faintest warmth carried across interstellar space. And yet a quiet scientific uncertainty remains. Although models predict trillions of cometary bodies populating the Oort Cloud, their precise number and size distribution are unknown. Observations of long-period comets entering the inner solar systems suggest a vast reservoir, but whether that reservoir contains more small bodies than large ones, or clusters them in specific regions, remains an open question. The Oort Cloud could be a smoothly distributed halo, or a patchwork of denser and sparser areas shaped by early gravitational events. Only future exploration still far beyond current technology could reveal its true structure. The narrator pauses at the surface of an imagined cometary fragment, its face rough and fractured, shaped by slow sublimation and past collisions. The cracks in its icy crust hint at pressures frozen in place, at gases that tried to escape, but were trapped again as temperatures plummeted. Only took a shift of a few degrees in orbital distance to freeze motion into memory. The scientific processes operating here unfold with glacial patience. A comet in the outer Oort Cloud moves so slowly that its orbital velocity might be only a few tens of meters per second. At such speeds, it would take millions of years to trace even a small segment of its full orbital arc. Meanwhile, cosmic rays continually bombard its surface, breaking chemical bonds and producing new molecules, some of which combine into complex organics. These substances darken the comet's surface, giving it a muted charcoal hue, that contrasts with the bright ices beneath. A poetic detail: when these organics accumulate over billions of years, they form a thin coating known as tholins, a rich carbon material that plays no role on Earth's surface, yet thrives in the absence of heat and oxygen. These substances may be among the most ancient unaltered materials in the solar system, their formation a slow response to cosmic radiation rather than any internal chemical process. Only took the constant drizzle of cosmic rays to paint a comet's surface in colours invisible to human eyes. Another soft observation arises from the rotation of these distant bodies. Many comets rotate irregularly, wobbling through space in what is known as tumbling motion. On Earth, such motion would be dampened quickly by friction, but here in near-perfect vacuum, tumbling persists for eons. A comet could wobble for the entire age of the solar system without ever settling into a stable spin axis. Only took the absence of air to make a wobble eternal. Deeper into this region, the narrator sees larger cometary bodies drifting like ancient seeds, some formed from mergers of smaller fragments, others sculpted by rare collisions that occurred before the Oort Cloud was even fully established. These collisions were gentle, more like slow compressions than impacts, because relative velocities were low in the distant solar environment. Merged bodies might contain layers of material from distinct origins, creating internal mosaics that record complex histories of early solar system scattering. Yet another uncertainty lingers here. The shapes and internal structures of Oort Cloud comets are unknown. NASA studies of closer comets suggest that many are contact binaries, two bodies that gently merged, but whether this holds true for Oort Cloud objects remains unclear. Their formation environment was colder, slower, and less chaotic, meaning they might preserve interior features long erased in more active regions. Only took the quietness of deep space to preserve structures no human has seen. As the narrator glides onward, the cometary bodies thin slightly, though still numerous enough that orbital simulations can infer their presence. Their silence becomes the defining texture of this region. No sunlight reaches them in meaningful strength. No solar wind shapes their surfaces. No gravitational force dominates their paths with urgency. Each comet drifts in its own ancient rhythm, a fragment of cosmic architecture suspended in cold equilibrium. And as this slow procession continues, the narrator prepares to move deeper into the Oort Cloud's slowly fading boundary, where the influence of the sun diminishes into something more like suggestion than force, and where the edge of the solar system becomes an expression not of distance but of gentle uncertainty. The narration drifts onward into a region where distance itself becomes a kind of silence, a place defined not by objects but by the absence of clear boundaries. Here, at the outer rim of what scientists call the solar system's gravitational sphere, the idea of a boundary without a line becomes the guiding sensation. There is no marker, no sudden shift, no definitive line separating the domain of the sun from the vastness of the galaxy beyond. Instead, the transition unfolds gradually like the soft blending of dusk into night, a slow diminishing of influence rather than a clean departure. Only took a few billion years for this non-boundary to settle into the shape it holds now. As the narrator moves through this space, the sun has already shrunk to a point of faint light, indistinguishable from many other stars except through a quiet sense of familiarity. Its gravity remains present, but at these enormous distances its pull becomes gentle, almost hesitant. Other stars exert their own subtle tugs, their influences weaving into the sun's gravitational field in ways that complicate any attempt to define where one dominion ends and another begins. This is the scientific truth guiding this section. The borders of the Oort Cloud and the solar system's gravitational reach are diffuse, determined not by physical edges, but by the ever-changing balance between solar gravity and the galactic tide, as well as the periodic influences of passing stars. The irony is that the solar system's edge exists precisely because it cannot be drawn. Only took the galaxy's slow mechanics to make a border that refuses to be a border. The narrator drifts through this transitional space, observing how even the sparse cometary bodies here reflect the ambiguity of their environment. Their orbits stretch into shapes so elongated that some take millions of years to return toward the inner system, if they ever return at all. Others hover on trajectories balanced so precariously between gravitational influences that any passing star or even a massive molecular cloud drifting through the Milky Way could nudge them away forever. Only took one stellar encounter to scatter millions of ancient fragments into new paths. A poetic detail arises from the faint density of interstellar particles here. Hydrogen atoms drift through the darkness unbound by solar wind pressure, moving in quantities too small to be called a gas, but too numerous to be considered absence. These atoms represent the material of the galaxy itself, and as they wander through the sun's faded influence, they offer a hint of the interstellar medium's presence, a diffused, expansive backdrop against which the Oort Cloud's outermost bodies drift. Yet a quiet scientific uncertainty remains the precise distance where the sun's gravitational influence fully yields to the galactic tide is unknown. The Hill sphere, an approximation of that boundary, extends roughly 1 to 2 light-years from the sun, but this estimate shifts depending on local stellar density, the movement of the sun around the Milky Way, and even encounters that have not yet occurred. The edge of the solar system is therefore both immensely large and fundamentally ambiguous, its shape moulded by events that unfold over spans so long they defy ordinary intuition. Only took the galaxy's quiet breathing to hint at edges we cannot see. As the narrator continues onward, the environment feels less like a structured part of the solar system, and more like a mingling region, a place where influences overlap. The sun's diminishing force becomes a subtle background pull, while the gravitational fields of distant stars rise gently in significance. At this distance, the narrator imagines the slow geometry of forces blending like overlapping ripples on a vast, calm lake. There is no boundary, only gradients. On human scales, gradients are gentle. On cosmic scales, they govern everything. A soft analogy emerges. It is like trying to determine the exact moment when a whisper becomes silence. You can sense the change, but no single instant can be named. So it is with the Oort Cloud's limit and influence that shades into the galaxy without sharply yielding to it. The narrator passes a lone cometary body, its orbit barely held by the sun's feeble pull. If a passing star shifts its velocity by even a tiny fraction, its future could diverge into 2 possibilities. It may fall inward again, crossing the planetary regions after millions of years, or it may drift outward, leaving the solar system entirely becoming an invisible wanderer in the spaces between stars. Only took one gravitational whisper to reshape a comet's fate. This transitional region holds another irony. While the inner planets form a tightly bound system, governed almost exclusively by the sun, the outermost components of the solar system experience a democracy of forces where the sun's authority competes with that of the broader galaxy. Comets out here live under multiple influences, yet none of those influences are strong. They move not according to any central plan, but according to the slow interplay of vast-scale dynamics. The narrator senses this interplay in the faint curves of trajectories that crisscross through darkness, each defined by slight variations in position and speed. Over billions of years, these variations accumulate into entirely new paths, tracing patterns that defy simplicity. Scientists model these motions through complex numerical simulations, but even the most advanced models must make assumptions because the initial conditions of each comet's orbit are unknown. And so a quiet scientific mystery persists. How many cometary bodies are lost to interstellar space in each galactic rotation? And how many new ones are gained? Passing stars not only remove objects from the Oort Cloud, but may deposit foreign ones, a slow exchange that has occurred countless times since the solar system formed. Only took the galaxy's wandering stars to create a halo shaped by both loss and gain. The narrator drifts deeper, observing how the absence of a boundary becomes its own kind of structure. There is something serene in the way influence fades without ending, something patient in the way forces overlap without resolving into clarity. This region does not behave like a border. It behaves like the soft blending between cosmic environments. And in this blending, the Oort Cloud's outermost domain begins to feel like an expression of the galaxy, rather than the solar system alone, a place where cosmic time stretches so far that even orbital mechanics feel suspended. Only took billions of years to create a space defined by neither belonging nor departure. The narrator lets this silent ambiguity settle, preparing to drift farther outward into the realm where even these faint cometary bodies become sparse, and where the slow motions of the galaxy begin to reshape the cloud more noticeably than the distant sun ever could. The narration drifts deeper into the vast open dark where the faint presence of the sun weakens into something closer to memory than force. And in this remote expanse, the slow, unhurried patrol of stellar winds becomes the defining texture. These winds are not the familiar solar wind that streams outward close to the planets. By the time they reach this far-flung frontier that flow is thinned into nothingness, its particles scattered across distances too wide for a coherent stream to persist. But other winds, older, broader, and belonging to the galaxy itself continue to move through the region with patient inevitability. The galactic tide born from the slow rotation of the Milky Way and the density of surrounding stars stretches the Oort Cloud gently a soft gravitational pressure that subtly shapes trajectories over spans too long to imagine. Only took the galaxy's slow turning to sculpt the cloud's contours. As the narrator glides through this quiet region, the rare cometary bodies drift with such lethargy that their motion becomes an idea rather than a visible fact. They respond to influences not in hours or days, but in tens of millions of years. Even a slight passing breeze of gravitational force from a star half a light year away could over time bend an orbit by enough to redirect a comet inward, setting it on a path that will take millions of years to unfold. The scientific fact anchoring this region is the role of the galactic tide, a weak but pervasive gravitational field created by the mass of the Milky Way's disk halo and spiral structure. This tide subtly raises and lowers the perihelia of Oort Cloud objects, altering their orbits in cycles lasting hundreds of millions of years. It also sets the overall shape of the cloud, stretching it slightly toward the galactic centre. Only took the faint background gravity of 100 billion stars to give the Oort Cloud its spherical form. These effects are gentle, nearly imperceptible in any human sense, but their scale is vast and their influence persistent. A poetic detail emerges from the way these tides act across time. The galaxy moves like a slow breath, expanding its influence outward, and then drawing it inward again as the sun drifts through the spiral arms. The tide's rhythm is not measured in seasons or years, but in revolutions around the galactic centre, each orbit taking more than 200 million years. During each cycle, the Oort Cloud shifts slightly, as though responding to currents in a deep invisible ocean. Only took one galactic year to realign the frozen halo surrounding the sun. Yet uncertainties remain in this quiet science. While astronomers understand that the galactic tide influences the Oort Cloud, the precise magnitude of its effects is not fully known. The density of the Milky Way's disk varies with location, and the sun's exact vertical oscillation relative to the galactic plane is still a topic of research. These uncertainties mean that the details of how often and how strongly the tide sends comets inward is not precisely determined. Some models suggest periodic increases in cometary influx linked to the sun's motion. Others argue the pattern is far more irregular. Only took the complexity of galactic structure to keep the Oort Cloud's behaviour partly hidden. Passing stars add further subtlety to the picture. Every few 100,000 years a star drifts close enough to the sun, close in a galactic sense, meaning within a few light years, to exert a tiny gravitational nudge on the cloud. Over billions of years, these nudges accumulate like soft taps on an ancient bell. Most have little effect, but occasionally one is strong enough to dislodge comets from their orbits, sending them inward on long descending trajectories. Only took a quiet stellar encounter to awaken a comet that had been asleep for 4 billion years. The poetically muted irony is that most of these passing stars are never seen by human eyes. They move in silence, their influence is felt across timespans longer than the entire history of complex life on Earth. A few stars, like Schultz's star, passed through the outer Oort Cloud in the deep prehistoric past, its faint gravitational field stirring objects along its path. The event unfolded without witness, without sound, without any visible trace, except for the slow redirection of frozen bodies into orbits that would only reveal themselves millions of years later. The narrator continues drifting through the dark, noting how even the galactic cosmic rays, high-energy particles that sweep through space at nearly the speed of light, play a minor role in shaping comets here. Cosmic rays bombard surfaces with steady inevitability, darkening them with complex organic residues and shifting their chemistry at the molecular level. These effects do not reshape bodies dramatically. Instead, they accumulate in slow layers, like the faintest frost settling over ancient ground. Only took the persistent drizzle of cosmic radiation to alter surfaces older than continents. A modern analogy drifts softly into the narrative. These forces act like the tides and breezes of an ancient Earth, altering landscapes, slowly shifting grains of sand over long seasons. But out here, the seasons span geological epochs, and the breezes come not from air, but from gravity and interstellar drift. The narrator imagines the slow passage of the sun through different regions of the Milky Way, moving through dense molecular clouds, open clusters, and the faint interarm spaces. Each environment changes the balance of forces, slightly adjusting the intensity of cosmic rays, the background gravitational field, and even the density of passing dust. These changes imprint themselves faintly onto the Oort Cloud, giving it a kind of cosmic weather, unfelt, unseen, but real across aeons. A scientific detail adds further depth. Simulations show that the outer Oort Cloud is more susceptible to galactic influences than the inner portion, whose orbits are more tightly bound. As a result, the outermost comets may be continually replenished by objects scattered outward from the inner cloud, while those in the outer envelope may be lost to interstellar space. And so the Oort Cloud becomes not a stable shell, but a constantly shifting halo, slowly exchanging material with the galaxy itself. Only took the vastness of time to turn the boundary of the solar system into a place of quiet trade. Yet a scientific mystery persists: how many of the comets in the Oort Cloud originated in other star systems. Models of early solar evolution suggest that the Sun formed within a dense stellar cluster, where nascent stars passed close enough to exchange material. During this chaotic era, some comets in the Oort Cloud may have been captured from neighbouring protostellar systems, their origins lying not in the Sun's nebular disk, but in the distant chemistry of alien suns. Only took the early crowding of stars to seed the solar system with foreign ice. The narrator drifts onward, feeling the presence of these forces not as a movement, but as a pressure dispersed across time, a field of influence that gives shape to the cloud without ever announcing itself. Comets here do not react quickly. They respond slowly, adjusting their orbits in ways that only make sense across epochs. The stillness is absolute, not because nothing happens, but because the happenings unfold at a scale too wide for any moment to contain. And so, as the narrator moves deeper into the frozen halo, the galactic tide's gentle patrol becomes both the structure and the story, a reminder that even far beyond the reach of planets, the universe continues to shape the solar system in ways that remain quiet, patient, and unresolved. Only took the universe's calm persistence to sculpt a realm where motion hides itself in stillness. The narration drifts farther outward into a region where the darkness feels less like emptiness, and more like an old archive, a place where ancient clues from the sun's earliest environment still linger in silence. Here, among the frozen bodies that populate the Oort Cloud, the echoes of the solar nursery persist in subtle signs, chemical fingerprints, isotopic traces, and long-preserved materials that recall a time when the sun was not yet alone, when it grew within a crowded cradle of newborn stars. The narrator moves slowly through this deep, still space, where each comet and fragment carries the faint memory of the environment that shaped it. Only took the universe a brief 10 million years to create the cluster that formed the sun, and then billions more to let its remnants drift into the quiet halo we now explore. The scientific fact that anchors this region is straightforward yet profound. Most models of star formation indicate that the Sun emerged within a dense stellar nursery, likely containing several thousand other young stars packed far more closely than stars appear in the present-day solar neighbourhood. Evidence supporting this comes from isotopic anomalies found in meteorites' short-lived radioactive isotopes, such as aluminum-26 and iron-60, suggesting that a nearby supernova occurred shortly before or during the formation of the early solar system. These isotopes would have decayed away in a few million years, meaning they must have been injected directly into the Sun's protoplanetary disk, during its earlier stages long before any planet solidified. A poetic detail arises in imagining that supernova's contribution, a shock wave rippling through the dense cloud of gas where the young Sun was forming, compressing some regions, dispersing others, adding heat and momentum to the swirling material that would become planets, moons, asteroids, and eventually the still distant bodies now drifting at the edge of the Oort Cloud. Only took the death of a massive star to shape the birth of our small one. The icy fragments out here preserve hints of that early environment. Some contain anomalous ratios of oxygen isotopes not matched elsewhere in the solar system, suggesting they formed from materials that existed in the early disk before it became fully mixed. Others contain crystalline silicates requiring temperatures far higher than any that existed where these objects formed, implying they must have originated close to the Sun and were transported outward by powerful winds or jets from the newborn star. This quiet irony rests in plain sight. Materials forged near the blazing heat of the proto-Sun now drift in the coldest region of its domain. Only took the turbulent winds of early solar formation to send these crystals on a journey of billions of years. Yet among these preserved clues lies a scientific uncertainty that continues to intrigue researchers. How exactly did material from the Sun's inner disk find its way to the far outer regions where the Oort Cloud eventually formed? Multiple mechanisms have been proposed: turbulent mixing in the early disk, gravitational scattering by giant planets, even violent ejections during the chaotic early formation of Jupiter and Saturn. But no single model accounts for all observed evidence. It remains unclear how material that formed within a few astronomical units of the Sun travelled outward by a factor of thousands or tens of thousands without being destroyed or incorporated into other bodies. Only took one unsolved question to keep the early history of the solar system partly hidden. As the narrator drifts deeper into the quiet expanse, the sense of the Sun's early environment becomes clearer in the mind's eye. A once crowded nursery, filled with newborn stars, some bright and massive others, dim and cool, all packed so tightly that the distance between them could be measured not in light years, but in mere fractions of one. The young solar system would have felt their presence in radiation winds and gravity forces that shaped its edges long before the Oort Cloud existed. Only took a few million years for that cluster to disperse, releasing the Sun into the broader galaxy, leaving behind the faint isotopic footprints still found in far-flung cometary bodies. The narrator imagines the last moments before the Sun drifted out of its birth cluster, when the combined gravity of neighbouring stars was still strong enough to shape the early distribution of icy bodies. Some models suggest that the very existence of the Oort Cloud required the Sun to spend time in such a dense environment. Without those early stellar encounters, the comets now drifting in this halo might never have been scattered to such extreme distances. Instead, they could have remained within the giant planet region, altering planetary formation and perhaps preventing the emergence of stable orbits like Earth's. Only took the crowded youth of the Sun to cast the seeds of the Oort Cloud into deep space. A gentle modern analogy drifts through the narration. The early solar system was like a young tree growing in a dense forest, shaped by the proximity of others before eventually standing alone in a wide open plain. The early pushes and pulls from neighbouring stars no longer act on it today, but their influence remains embedded in the structure of the distant halo now surrounding it. As the narrator moves past an imagined cometary fragment, its surface shows signs of this ancient story. Darkened by cosmic rays, its interior remains pristine, preserving volatile compounds and dust grains from the earliest eras. Some of these grains show ratios of nitrogen and carbon, suggesting origins in environments exposed to intense ultraviolet radiation conditions, typical of a star-forming region illuminated by massive young stars. These preserved clues whisper of a time when the Sun and its siblings shared a common envelope of gas and dust. Yet another uncertainty lingers quietly: how many of the Oort Cloud's objects began their journey not in the solar system at all, but in the disks of neighbouring young stars that passed close to the Sun during its birth. Some simulations suggest that a significant fraction, perhaps 10% or even more, of the Oort Cloud's population may be interstellar in origin, captured during the chaotic interactions of the early cluster. Only took one stellar close pass to add foreign objects to the Sun's distant reservoir. This possibility deepens the quiet poetry of the region. If true, then drifting among the ancient comets are objects that formed around alien suns containing chemistry, shaped by different environments, different temperatures, different histories entirely. These fragments would not simply echo the Sun's nursery, they would whisper of nurseries long lost to the galaxy's rotation. The narrator glides through this thought, letting it settle without resolution. Scientific understanding of these early exchanges remains incomplete, limited by both the difficulty of modelling such vast timescales and the lack of direct observational access. And so this region becomes not only a repository of early solar material, but also a quiet reminder of how interconnected the young galaxy once was. Only took the galaxy's long drift to separate siblings that once formed together. As the narrator moves farther outward, the echoes of the Sun's birth fade into the background, but the materials themselves remain frozen unchanged, carrying signatures of that early era across 4.5 billion years. The Oort Cloud becomes both archive and after-image, both relic and consequence. And in this still cold halo, the story of the Sun's earliest moments lingers softly preserved in ice dust and silence too deep for time to erase. The narration drifts into a deeper sweep of darkness, where the space between cometary bodies grows wider, and yet each one holds its place with a kind of quiet insistence, as though anchored more by time than by gravity. Here in these far outer regions of the Oort Cloud, the prevailing sensation is dormancy, a stillness so complete that even the word motion feels overly ambitious. This is where most comets never wake. They drift through the cold for billions of years, locked in orbits so immense and so slow that entire eras of Earth's history pass without these bodies moving even a fraction of their ancient paths. Only took 4 billion years for this vast stillness to appear natural. The scientific fact defining this region is simple. The majority of comets in the Oort Cloud will never return to the inner solar system. Their orbits extend so far that a full cycle would take millions or even tens of millions of years, and many are destined never to complete a single orbit at all before being nudged outward into interstellar space by passing stars or the faint tug of the galactic tide. Some comets will drift until the Sun itself exhausts its nuclear fuel and swells into a red giant. Only took the slow mechanics of orbital dynamics to make lifetimes irrelevant for frozen bodies. The narrator approaches one imagined comet, a fragment of primordial ice, perhaps 5 or 10 kilometers across. Its surface is a deep charcoal grey, darkened by organic residues accumulated over eons. Cosmic rays have altered the topmost layers, creating a brittle shell only a few centimeters thick. Beneath that shell lies a mixture of ice's water, carbon monoxide, carbon dioxide, methane ammonia, frozen together into a matrix so cold and rigid that it feels more like stone than ice. But the interior tells a different story, porous, fragile and ancient, a place where volatiles rest unchanged since the earliest days of the solar system. A poetic detail settles softly in the mind. The gases locked inside these depths have not moved in billions of years. They sit in cavities and pores trapped by the sheer absence of heat, awaiting a warming that will never come. Only took a universe of cold to freeze breath itself into silence. The narrator imagines the slow orbit of this dormant body. Its velocity is so small that it could take thousands of years to move a single degree along its path. The stars shift around it far more quickly than it shifts around the sun. Geological epochs pass unnoticed. Continents rise and fall. Oceans advance and retreat. Life evolves from simple cells to complex organisms, and this comet remains almost exactly where it was, its motion measurable only through phenomena invisible on human timescales. Only took Earth's entire evolutionary history for a comet to begin the slightest descent toward the Sun. Yet amid this stillness, a quiet scientific uncertainty persists. Scientists cannot determine precisely how many dormant comets populate the Oort Cloud. Estimates range from hundreds of billions to trillions. The outermost boundaries of the cloud remain impossible to measure directly, leaving its contents inferred from statistical models of long-period comet appearances. Even its shape is not perfectly known, slightly elongated perhaps, or more spherical, depending on how much material remains undetected in the farthest reaches. The cloud may be far more massive or far more sparse than current models predict. Only took our limited vantage point to leave the cloud partly unknowable. These uncertainties blend into the narrative as the narrator drifts from one dormant body to another, observing subtle variations. Some comets appear smooth, their surfaces rounded by ancient sublimation events that likely occurred long before Earth's crust solidified. Others are jagged, fractured by cosmic impacts so gentle that their mechanical scars remain preserved for billions of years. Yet others show no visible features at all, darkened entirely by tholins absorbing nearly all light that touches them. The absence of activity becomes a defining attribute. No jets, no sublimation, no rotating fountains of gas and dust. Only took the absence of heat for comets to become forgotten stones in the dark. A modern analogy emerges softly. These bodies resemble seeds carried far from their parent tree but dropped into a region so cold that germination is impossible. They hold all the ingredients, all the chemistry that gave rise to the dynamic behavior of comets in the inner solar system, yet they remain forever dormant. The narrator drifts closer to a fractured ridge, the boundary between two icy layers. These layers record the slow freeze-out of materials as the young solar system cooled. They form a subtle geological record preserved without erosion, without disturbance, without any external process to reshape them. Only took the stillness of deep space to preserve memories more ancient than rock. But even in this profound calm, faint forces persist. Cosmic rays continue to break chemical bonds at the surface. Micrometeorites, tiny fragments of ancient dust, occasionally strike the outer layers, releasing minuscule amounts of energy and creating microscopic craters. Over billions of years, these events darken surfaces, further deepen their brittleness, and add subtle complexity to the topmost layers. Yet the overall form of each comet remains unchanged. The narrator considers the potential energy locked within these long-frozen objects. Should one of them ever descend toward the inner solar system, its once quiet ices would warm, expand, and erupt into active jets. The same volatiles that lie dormant now would burst forth in long tails of gas and dust, illuminating the sky for observers on a distant planet. But the vast irony is that most will never receive this warming. They will remain frozen archives of the solar system's youth, drifting through a realm where sunlight arrives only as a symbolic presence. Only took one rare gravitational nudge to determine whether a comet ever wakes. The narrator moves away from the imagined body, returning to the slow, indistinct drift of this far halo. The density of comets increases slightly here, though still so sparse that each one remains separated by millions of kilometers. Their distribution feels like a vast diffuse constellation of sleeping relics, each one bearing witness to a different chapter in the solar system's birth and early evolution. A scientific detail adds depth. Some dormant comets in the Oort Cloud may contain preserved organic molecules older than Earth itself, perhaps even prebiotic compounds that once drifted through the molecular cloud that collapsed to form the Sun. These molecules have not been altered by heat, by atmospheric reactions, or by chemical processes. They remain as they were, a snapshot of chemistry, as it existed before any planet took shape. Only took the absence of geological processes to preserve molecular histories billions of years old. A quiet uncertainty hovers around this idea. Scientists do not yet know how complex these preserved organics might be. Some cometary samples from missions like Rosetta and Stardust revealed amino acid precursors and complex hydrocarbons, but those samples came from comets that had already undergone significant heating. The true earliest organics remain hidden in frozen interiors inaccessible until a future mission reaches the distant cloud, something no spacecraft has yet attempted. Only took our technological infancy to leave these molecular archives unexplored. As the narrator drifts onward through the stillness, the quiet truth of this region settles softly into place. These comets are not merely unvisited, they are almost untouched by time. Their near total inactivity, their billion-year dormancy, their drifting silence all serve as reminders of how vast and patient the solar system truly is. Most comets will remain asleep until the sun itself fades, and in that profound stillness, the narrator moves on, ready to cross paths with the rare few that do awaken, tracing long arcs inward that may never repeat again. The narration drifts into a region where the silence grows even older, yet here a subtle shift begins to take shape, a faint pattern of motion so rare it feels almost accidental. This is where the dormant serenity of the Oort Cloud sometimes breaks, where a few long-period comets begin the slow inward journeys that will one day bring them close to the sun. These are the rare visitors returning home, though home is only a poetic convenience. Most of these bodies have never been near warmth before. Their inward arcs begin not with drama, but with the smallest gravitational persuasion, the kind of influence so gentle it might take 1,000,000 years to manifest. Only took a whisper of gravity to send a comet inward after billions of years of stillness. The scientific fact that anchors this region is clear long-period comets observed from Earth originate almost exclusively from the Oort Cloud, displaced from their distant orbits by the galactic tide or passing stars. Their paths are so elongated that one passage near the Sun may consume millions of years, while the return journey, if it occurs at all, might require tens of millions more. Only took one alignment of distant forces to write a path that crosses the inner solar system once in a geological epoch. The narrator approaches an imagined comet beginning such a long descent. It drifts quietly, almost indistinguishably from its dormant neighbours, except for the slightest curvature in its path, a shift invisible in any moment yet certain over time. As it moves slowly sunward, nothing immediate changes. The temperatures remain unimaginably cold. The surface stays still dark and inert. Not until it has descended thousands of astronomical units will the faintest warmth begin altering its chemistry. For now, it sleeps even as it moves. A poetic detail emerges in the shape of its orbit so long, so stretched, that the sun occupies only the tiniest segment of its path. The comet spends nearly all its existence in darkness, with the briefest sliver of time spent in the realm where comets become visible. Only took a few million years to reach the region where waking begins. Scientists describe these paths with precision-high eccentricities perihelia calculated far inside the planetary region. But the lived experience of the comet, if such a concept can be imagined in purely physical terms, remains one of timeless drift. These rare bodies hold material unchanged since the early solar system hardly altered at all by the cold. Even as they descend inward, the sublimation of ices remains dormant until the temperature crosses certain thresholds. Only took the faintest increase in sunlight to begin the cascade that creates a comet's brilliance, though that brilliance lies far ahead on its journey. Yet a quiet scientific uncertainty persists. Astronomers cannot predict which specific Oort Cloud objects will be nudged inward at any given time. The motions are too slow, the influence is too subtle, the initial conditions too uncertain. While models can estimate the expected frequency of long-period comets entering the inner solar system, roughly a few per year, the identities of those objects remain unknown until they are already far along their inward path. Only took the limitations of knowledge to keep the cloud's awakenings forever unpredictable. As the narrator glides with the imagined comet, another subtle irony reveals itself despite billions of years frozen in darkness. The comet contains within its structure clues to the earliest chemical processes that occurred in the solar nebula. Some of the ices locked within it contain ammonia, hydrates methanol, and even complex organic molecules believed to have formed through photochemical reactions in the early disk. These compounds, stable at the coldest temperatures, retain atomic arrangements that record the conditions from which they formed. Only took 4.5 billion years of cold storage to preserve the chemistry of the Sun's infancy. The narrator imagines this rarity continuing its slow inward spiral. At first, cosmic rays continue to shape its surface chemistry, darkening it further. Occasionally, micrometeorites strike with such small energies that they barely dent the crust. But as the comet enters regions where sunlight is slightly stronger, still unimaginably weak on human scales, but warmer than absolute zero, the outermost ices begin to change state. Not sublimation, not jets, not yet, but microscopic rearrangements. Amorphous ice begins to crystallize. This transition releases trapped gases, building tiny pockets of pressure inside the crust. These changes occur over tens of thousands of years, marking the earliest phases of the comet's awakening. Only took a subtle structural shift to signal that the long journey inward has begun. A scientific detail enriches this stage. The crystallization of amorphous ice into a more stable crystalline form occurs around 120 Kelvin, far below the temperatures where visible cometary activity begins. This process likely contributes to sudden outbursts observed in some long-period comets, even when they are still thousands of astronomical units from the Sun. These outbursts do not produce tails or comae, but instead alter the rotation and structure of the comet's crust. Only took a quiet internal rearrangement to change the path of a body older than Earth's continents. The narrator continues drifting alongside the comet as it enters the realm, where its orbit begins to accelerate, still slowly, still silently, but now perceptibly. Relative to the vast timescales of the Oort Cloud, the beginning of this descent feels almost lively. For the first time, the comet experiences slight thermal gradients across its surface. For the first time, the Sun begins to become more than a faint star among many. Only took a shift of a few dozen astronomical units to make the Sun noticeable again. Yet even as these changes unfold, questions remain unanswered. Scientists still do not know whether most long-period comets originate in the inner or outer Oort Cloud. They do not know how many are lost to interstellar space before they ever descend. They do not know whether comets entering the inner solar system today reflect the distribution of bodies billions of years ago, or whether gravitational interactions have reshaped the reservoir significantly. Every long-period comet that appears carries with it not only ancient material, but also unsolved physics. Only took the limits of observation to make each comet a mystery returning from the dark. The narrator glides onward, noticing faint drifts of dust along the comet's path particles shed, over time not through sublimation, but through tiny impacts and surface fractures. These faint trails contain grains older than the planets, grains that might one day drift into the inner solar system, or be captured by Earth's gravity. If they fall to the surface of a planet, they become micrometeorites, adding their ancient chemistry to the geological record. Only took a slow drift across billions of kilometers to carry primordial dust into a planet's sky. As the comet descends farther, the narrator senses that its journey, though slow beyond any human comprehension, has entered its only active phase in billions of years. The comet remains mostly asleep, no tail, no visible change, but the subtle warming continues. The materials inside begin to realign. Gases shift in their frozen cages. Cracks widen imperceptibly. Rotation speeds change by fractions. All these changes accumulate over vast distances, preparing the comet for the moment still far ahead, when it will begin shedding its ancient materials into space. And so the narrator follows this rare visitor through the earliest phase of its awakening, watching as it moves from the outermost quiet of the Oort Cloud toward the delicate boundary where sunlight begins to reclaim influence. Only took the smallest of galactic nudges to send a relic of the solar system's birth on its extraordinary return. The narration drifts farther into the dim halo where the Oort Cloud's frozen stillness becomes part of an even deeper rhythm, one governed not by the sun but by the slow gravitational breathing of the Milky Way itself. Here, far beyond the reach of warmth, the galaxy exerts its quiet influence through tides so gentle that their effects are nearly invisible moment by moment, yet so persistent that they reshape the cloud across epochs measured in hundreds of millions of years. This vast modulation, subtle and continuous, guides the long-term motion of the Oort Cloud's ancient bodies. And so the next sensation in this drifting journey is the soft stirring of galactic tides like slow breathing. Only took the galaxy's patient inhalation and exhalation to move fragments older than continents. The scientific fact grounding this region is the role of the Milky Way's gravitational field, a field so enormous and diffuse that it affects every object bound to the Sun, especially those in the distant outer shell of the Oort Cloud. This field does not act like a single directional pull, but rather like a slow bending of space, gently stretching or compressing orbits, depending on the Sun's position relative to the galactic plane. As the solar system oscillates above and below that plane every 30 to 40 million years, the strength and orientation of the galactic tide shift as well, altering cometary orbits in ways that appear almost abstract on human scales. Only took one vertical oscillation through the galaxy's disk to reshape millions of ancient trajectories. The narrator drifts through this gravitational sea, sensing the way each comet responds differently, depending on its distance, mass orientation, and initial speed. The outermost bodies, loosely bound, fragile in their association with the Sun, are especially sensitive to these tides. An orbit inclined differently from its neighbours may experience a slightly stronger stretch, while another aligned with the galactic centre may feel a gentle compression. These influences are so subtle that a single orbit might take millions of years to reveal their shape. Yet over hundreds of millions of years, the effect becomes profound. Some comets are nudged inward, others drift outward, eventually leaving the solar system altogether. Only took the Milky Way's slow winding to decide a comet's place in or out of the Sun's domain. A poetic detail arises from the way the galaxy's mass is arranged. The Milky Way contains not just stars but dark matter, an invisible, elusive form of mass that exerts gravity without emitting or reflecting light. The Oort Cloud, drifting in the outer portions of the Sun's gravitational reach, moves through a region where this dark matter halo exerts a subtle but steady influence. Though the density of dark matter may seem low, the scale of its presence across hundreds of billions of kilometers gives it a faint but cumulative pull on cometary orbits. In this sense, the Oort Cloud's frozen bodies feel the presence of matter no human eye can see. Only took unseen mass to guide the motions of unseen comets. Yet a quiet scientific uncertainty remains. Astronomers cannot precisely determine the structure of the galactic tide because the Milky Way's mass distribution, especially the distribution of dark matter, is not fully known. Estimates vary, models conflict, and the Sun's exact path through the galaxy adds another layer of complexity. As a result, predictions of how often the galactic tide should send comets inward are approximate at best. Some theories link periodic mass extinctions on Earth to increased comet influx driven by these oscillations, but the evidence is far from settled. The uncertainty remains a reminder that the galaxy shapes the solar system in ways still not fully understood. Only took a hidden gravitational landscape to keep the cloud partly mysterious. The narrator drifts past a small cluster of cometary bodies, an unusually dense patch of objects that share similar orbits. These clusters may have formed from ancient collisions or from the gravitational capture of fragments during the early solar system's cluster phase. Their proximity to one another creates yet another layer of complexity in the galactic tide's influence, as nearby bodies can subtly reshape each other's paths through long-term gravitational interactions. This interdependency introduces faint instabilities that can amplify over millions of years. Only took a slight imbalance among neighbours to redirect a fragment into a new trajectory. As the narrator observes, the whole halo feels suspended within a larger geometry, like dust drifting in a vast, slowly turning room. The Sun's orbit around the Milky Way takes more than 200 million years, and during that time the solar system passes through regions of varying stellar densities. In denser regions where star populations are greater, the gravity acting on the Oort Cloud increases. In sparser regions, it decreases. These changes are gradual, distributed across spans far beyond any single comet's lifetime, yet their effects accumulate. A soft analogy arises: the galaxy's rotation acts like a deep, slow tide in an ocean too vast to grasp, shaping the motion of swimmers who will never know the shoreline. Only took one galactic year to shift a comet's future by millions of kilometers. A scientific detail adds further nuanced numerical models show that the galactic tide is particularly efficient at modifying the orbits of comets, whose aphelia, the farthest points in their orbits, lie in the outermost reaches of the Oort Cloud. These bodies can have their perihelia lowered dramatically over long timescales, sometimes sending them on inward plunges. This phenomenon helps explain why long-period comets enter the inner solar system from all directions, forming a nearly isotropic distribution in the sky. Only took the galaxy's broad gravitational shape to distribute comets evenly across the heavens. As the narrator drifts deeper, the faint motion of individual comets becomes increasingly difficult to distinguish from the background. Everything moves so slowly, yet everything moves. The galaxy's tidal influence is continuous reshaping orbits without ever producing visible acceleration. And in this environment, the distinction between movement and stillness loses meaning. A comet drifting at tens of meters per second may seem motionless, while the galaxy itself moves at hundreds of kilometers per second through the cosmic background. Motion in one context becomes stillness in another. Only took a shift in scale to make speed appear as rest. Yet amid this delicate interplay, another uncertainty lingers. How does the Oort Cloud respond to interactions with large-scale structures like spiral arms or giant molecular clouds? Some theories propose that passing through denser regions of the galaxy could briefly increase the tidal force, triggering waves of inward-bound comets. Others suggest the effect is weaker or more diffuse. Without direct observation of the cloud, these questions remain suspended in theoretical space, unresolved but quietly influential. Only took the galaxy's vast complexity to keep the cloud's deepest rhythms hidden. A poetic image emerges as the narrator contemplates the slow influence of the galactic tide. The Oort Cloud stretches subtly, like a halo of frozen seeds stirred by the faint breath of a sleeping giant. Its shape is not static, but shifting, responding to forces that act without urgency. Some comets drift closer to the Sun, others drift outward, and still others maintain their positions for billions of years. No single moment defines these changes. Their meaning exists only across spans of time so enormous they dissolve individual epochs. Only took cosmic patience to let motion and rest blend into one. And so the narrator continues moving through this vast gravitational landscape, sensing how the Milky Way's quiet breathing shapes the frozen architecture of the far solar system. The comets drift on indifferent to their rare awakenings, responding not to moments, but to ages. And in this immense stillness, the galaxy's influence remains constant, soft, slow, and unending, sculpting the cold halo that surrounds the Sun like a distant ancient memory. The narration drifts onward through the dim and ancient quiet, entering a part of the Oort Cloud where distance begins to lose meaning, and the frozen bodies grow so sparse that each one feels like its own isolated world. Here, amid this immense expanse, the guiding sensation becomes chance, the faint coincidence of trajectories encounters, and long-forgotten motions that slowly shape the architecture of this icy halo. This is where the Oort Cloud's form reveals itself as a sphere shaped by chance, composed of fragments scattered in every direction, not by design, but by the deep chaotic history of the early solar system. Only took a few chaotic millions of years at the solar system's birth to create patterns that persist across billions. The scientific fact grounding this section is straightforward. The Oort Cloud's spherical shape is not an inherent feature of the Sun's formation, but a statistical result of countless gravitational interactions. When the giant planets formed Jupiter-Saturn, Uranus and Neptune, their massive gravities flung countless icy planetesimals outward. Some escaped completely into interstellar space, while others settled into distant orbits. Over time, the influence of passing stars and the galactic tide randomized these orbits, further turning what was once a disk-like scattering into a shell surrounding the solar system. Only took a series of ancient gravitational tosses to populate the cloud in every direction. As the narrator moves through this sparse halo, the space feels almost empty, and yet every few tens or hundreds of millions of kilometers, a lone fragment drifts by. Each object's orbit is a preserved accident, a quiet relic of long-past interactions. Some bear subtle signs of early collisional history. An angled ridge here, a faintly sheared surface there, features that result not from violent impacts, because out here velocities are extremely low, but from the slow merging or fracturing of icy bodies in the distant past. Only took a few gentle collisions billions of years ago to leave scars that will never erode. A poetic detail emerges in the silence between objects, a silence so vast that two fragments passing within 1,000 kilometers of one another feel like neighbors. In this emptiness, proximity itself becomes remarkable. And within that long quiet, the narrator imagines the slow exchange of faint gravitational tugs as bodies drift past one another across thousands of years. These interactions are too weak to produce immediate changes, yet over millions of orbits they accumulate, nudging trajectories ever so slightly. Only took patient, nearly invisible influences to sculpt paths older than any mountain on Earth. Yet a scientific uncertainty lingers here. How often do collisions actually occur in the Oort Cloud? The answer remains elusive. Models suggest that collisions are exceedingly rare, perhaps occurring only every few hundred million years for any given object. But the total number of bodies is unknown, and the distribution remains theoretical. If certain regions once held greater density, early collisions may have played a more significant role than current simulations assume. Conversely, if the cloud has always been extremely diffuse, many of its bodies may have remained essentially untouched since their formation. The balance between these possibilities remains unresolved. Only took the limits of observation to leave the cloud's collisional history incomplete. The narrator drifts near one imagined body, a small object, perhaps 2 kilometers across, shaped by gentle impacts in the ancient past. One hemisphere shows faint stratification layers formed by the accretion of dust and ice shortly after the solar system's birth. The other hemisphere shows a more chaotic topography, with ridges and valleys that likely formed during a slow collision with another body of similar size. Because relative velocities were low, this collision did not pulverize either object. Instead, it compressed and fractured them, merging their materials unevenly. Only took a slow-motion impact to permanently alter a frozen landscape. These structures give the cloud its hidden complexity. Though comets appear similar when viewed from the inner solar system, dark icy bodies, with elongated tails in the far Oort Cloud, each fragment possesses its own unique memory of early solar system history. Some are remnants of planet building that fail to join larger worlds. Others are ejected from regions near the young sun. Still others may be captured fragments from passing protostars in the sun's birth cluster. The Oort Cloud becomes a museum not of uniform objects but of frozen variety. Only took the solar system's earliest turbulence to scatter its ingredients into a halo of diversity. A modern analogy settles softly into the narrative. These bodies drift like ancient library pages torn from the same book, but but scattered by wind into distant corners of a quiet chamber. Their arrangement is not purposeful but incidental, shaped by long-forgotten breezes. Yet despite this randomness, a quiet pattern emerges. The overall spherical geometry remains upheld by the combined influence of the Sun, the galaxy, and the accumulated record of early interactions. As the narrator drifts deeper, the soft irony of this realm becomes clearer. The Oort Cloud is often imagined as a smooth sphere, yet its true structure is almost certainly uneven, denser in some regions, sparsely populated in others, shaped by irregularities in early scattering events, and by later influences from wandering stars. The cloud is both a structure and an accident order emerging from chaos not through design but through persistence across vast time. Only took 4.5 billion years of gravitational blending to turn ancient turbulence into present tranquility. Another scientific detail adds nuance to this image. When icy planetesimals were scattered outward by the giant planets, only a small fraction entered stable orbits. Most were either ejected from the solar system entirely or fell inward to collide with other bodies. The ones that survived became the seeds of the Oort Cloud. Their initial orbits were far from spherical. They were elongated, highly inclined, and often chaotic. Only after millions of years of galactic tides and stellar encounters did the orbits become randomized enough to approximate a spherical shell. Only took an entire galactic cycle to erase the memory of their initial directions. Yet even now, the spherical shape is not perfect. Subtle asymmetries persist, perhaps hinting at the early presence of nearby stars or the influence of passing objects like Schultz's star. If one region of the early cloud experienced more stellar encounters than another, its bodies might be distributed differently. Some researchers propose that certain directional asymmetries in long-period comet arrivals may reflect these ancient influences. Only took the uneven geography of the galaxy to leave soft fingerprints in the cloud's shape. The narrator passes a narrow grouping of fragments drifting along similar trajectories. These clusters might be the remnants of single-parent bodies that fractured billions of years ago, their pieces moving together ever since. Over long spans, the galactic tide may gradually separate them, but for now their shared arc remains. This faint companionship in an otherwise solitary region provides a quiet reminder of how random and delicate the cloud's organization truly is. Only took a single ancient breakup to send a family of fragments drifting through eternity. As the narrator moves away from this cluster, the stillness deepens once more. The immense emptiness between bodies becomes part of the story, revealing how little motion is needed to create structure across cosmic time. The shape of the Oort Cloud, vast spherical diffuse, is the final expression of billions of years of tiny accumulated influences. No event shaped it alone, no moment defined its borders. It is the sum of rare collisions, ancient scatterings, soft gravitational nudges, and the slow tidal breathing of the galaxy. Only took the smallest forces acting for the longest time to build the farthest structure of the solar system. And so, the narration continues drifting through this quiet geometry of chance, ready to explore how the delicate materials preserved inside these icy bodies carry deeper secrets about the earliest chemistry of the solar system, and how even here at the farthest reach the universe continues its patient work of shaping frozen time. The narration drifts deeper into the frozen halo, entering a realm where the darkness feels dense with memory, as though every particle and every frozen surface contains a record too ancient for any planet to recall. Here, the central sensation becomes one of preservation of ancient ice carrying fragile memory. It is in these deep unlit regions of the Oort Cloud that the chemical history of the early solar system rests suspended within the interiors of cometary bodies, untouched by warmth or geological activity for more than 4 billion years. Only took the universe's longest night to preserve the earliest whispers of the sun's beginning. The scientific fact grounding this region is clear. Comets contain some of the oldest unaltered material in the solar system. Unlike planets, moons, and asteroids which have undergone heating differentiation, weathering, or tectonic shifts, The comets of the Oort Cloud have remained cold and inert. Their interiors preserve organic molecules, frozen volatiles, noble gases and isotopic ratios that reflect the conditions of the solar nebula before any planet had formed. Only took the absence of geological processes to protect chemistry older than any terrestrial rock. The narrator drifts toward a single imagined comet larger than many in the region, perhaps 20 kilometers across. Its surface is pitch black, coated with tholins produced by cosmic rays over eons. These complex organics give the comet an almost velvet darkness, absorbing nearly all the faint starlight that reaches it. The outer layers, only centimeters thick, are brittle and fractured, shaped by the slow accumulation of radiation damage. But beneath that fragile crust lies an interior that has never known temperatures above the coldest extremes of interstellar space. A poetic detail arises in imagining the layers below the crust ancient porous matrices of water ice, mixed with carbon-rich molecules, ammonia ices, and tiny mineral grains. These layers were not laid down in seasons or cycles. They were formed in the primordial solar disk from accretion of dust and frozen gases, preserving not only chemistry, but geometry. Tiny pores, subtle gradients, and microscopic inclusions that record the earliest processes of condensation and aggregation. Only took 1 million quiet years at the dawn of the solar system to build the frozen memory now drifting in darkness. Yet within this deep preservation lies a scientific uncertainty that continues to intrigue researchers. How exactly are these organic molecules arranged? Missions like Rosetta revealed complex organics on the surfaces of short-period comets, but those bodies had already undergone heating near the Sun. The true earliest organics remain buried inside Oort Cloud comets, shielded from radiation and sublimation. Some may include amino acid precursors, polycyclic aromatic hydrocarbons, or nitrogen-rich chains formed through ultraviolet processing in the molecular cloud that predated the Sun. But the precise structures, how long the chains or whether chirality exists, how the molecules are distributed, remain unknown. Only took the difficulty of travelling thousands of astronomical units to keep the earliest chemistry hidden. As the narrator drifts past the comet's surface, the quiet irony settles lightly. These frozen interiors may contain answers to questions about the origin of life, yet they rest in a region so remote that no spacecraft has ever approached it. Comets that do enter the inner solar system provide only glimpses, surface layers altered by heat jets that expose only shallow interiors, dust grains that break apart before full analysis. The deepest material remains locked in the distant halo, waiting in perfect stillness. Only took the solar system's coldest refuge to guard secrets older than Earth's oceans. The narrator imagines moving closer to a fracture in the comet's crust. Inside the crack, the darkness deepens. Microscopic grains of pre-solar origin, tiny bits of matter formed in the atmospheres of dying stars long before the Sun existed, rest embedded within the ice. These grains carry isotopic signatures that reveal their origins in supernova red giants and other ancient stellar processes. Some contain excesses of oxygen. 17 or silicon-29 others show ratios of carbon and nitrogen that hint at their stellar pasts. This quiet mosaic of alien origins lies preserved inside a body formed around the young Sun. Only took the death of earlier stars to seed this small fragment of frozen memory. A modern analogy flows softly into the narration. The comet's interior resembles an archive of microscopic artifacts, each grain like a page torn from a much older story, gathered and frozen together by chance. Unlike libraries on Earth, where pages are arranged and catalogued, these cosmic archives exist in random clusters, preserved more by coldness than by intention. But even amid this stillness, faint processes continue. Cosmic rays penetrate a few meters into the surface, altering molecules, gradually turning simple carbon compounds into more complex organic residues. The deeper layers, however, remain untouched. Time moves in layers here. The outermost ice changes over tens of millions of years, the middle layers over billions, and the core not at all. Only took cosmic patience to stratify memory into frozen depths. A scientific detail deepens this view. Noble gases like neon and argon trapped within the comet's ice hold isotopic ratios that reflect the earliest conditions of the solar nebula. These gases do not bond with other atoms, making them faithful indicators of early solar chemistry. Yet they are extremely volatile, escaping with even slight warming, which means only comets that have never approached the Sun, the vast majority in the Oort Cloud, still contain these ancient gases. Only took 4.5 billion years of deep cold to preserve the universe's most delicate breath. Yet another gentle uncertainty arises. Scientists do not know whether volatile-rich comets form distinct populations within the Oort Cloud, or whether their distribution is random. Some models suggest that comets originating close to the Sun with lower volatile content were scattered outward, along with more volatile-rich objects formed farther away. Others argue that snowline gradients and disk temperature variations created natural distinctions that still exist today. The narrator considers that the answer may lie buried in the icy interiors drifting through this distant halo. Only took early solar gradients to lock unresolved diversity into the cloud. The narrator drifts past another imagined fragment, a smaller body irregularly shaped, perhaps only a few kilometers across. Its surface appears smoother than the first, coated with a fine layer of dust that settled during the earlier scattering events. Beneath that dust lies ice containing methane clathrates, molecules trapped within cages of water, ice structures that require extremely low temperatures to form and remain stable. These clathrates, fragile on Earth, have persisted here for billions of years. Only took cosmic refrigeration to maintain structures that no terrestrial environment could preserve. This frozen memory extends not only to chemistry but to rotational histories. Some comets have rotated slowly for billions of years, their axes drifting only slightly due to tidal influences or internal changes. Others wobble irregularly, their tumbling motion preserved by the absence of any external torque. These rotations, preserved across aeons, form records of early collisions and accretion events. Only took a frictionless vacuum to let a wobble persist longer than Earth's mountains. As the narrator drifts away from this fragment, the vastness of the region becomes palpable again. The emptiness stretches so far that even frozen memory itself feels like a rare treasure suspended in darkness. Each comet holds its own archive, its own chemical history, its own isotopic clues. Together these bodies form a distributed library of the early solar system, each volume drifting independently, none yet read in full. Only took cosmic silence to guard the oldest records of planetary origins, and so the narrator glides onward, sensing how every icy interior in this distant halo carries not just matter, but memory, ancient, fragile, unresolved. The journey continues deeper into the Oort Cloud's frozen expanse, toward a region where even interstellar visitors may drift through, adding their own silent stories to the Sun's distant archive. The narration drifts farther into the frozen dark, entering a region where the boundary between what belongs to the Sun and what does not becomes faint, porous, and quietly crossed. Here in this remote halo, the Oort Cloud is not an isolated reservoir, but a place where the solar system briefly shares space with travelers from elsewhere in the galaxy. These interstellar visitors pass through silently their paths, shaped not by the Sun's origin, not by planetary scattering, but by histories written in other stellar nurseries, other nebular disks, other cosmic beginnings. The guiding sensation becomes one of quiet coexistence, a halo shared with strangers. Only took the vast drift of stars to let foreign fragments wander across the Sun's far domain. The scientific fact grounding this section is simple yet profound. The solar system moves through the galaxy, and as it travels, interstellar objects occasionally pass near or through the Oort Cloud. The recent discoveries of Oumuamua in 2017 and Comet Borisov in 2019 confirmed what astronomers had long suspected, that fragments from other stars traverse our region of the Milky Way. These detected visitors passed much closer to the Sun, but countless others far fainter and smaller likely pass quietly through the Oort Cloud without ever approaching the planets. Only took our improved observations to reveal what had been happening for billions of years unseen. The narrator drifts through the vast emptiness where one such imagined visitor moves a small elongated shard of ice, its brightness subtle, its surface geometry unlike the typical bodies formed within the solar system's disk. Its orbit is hyperbolic, not bound to the Sun at all. It passes through the halo of cometary bodies like a quiet guest, wandering briefly through a silent hall, noticed by none of the frozen inhabitants around it. Only took one encounter with the Sun's gravity to bend but not capture its ancient path. A poetic detail emerges in how different its composition might be. Interstellar objects carry chemical signatures from stellar environments, wholly separate from the Sun's own history. Different metallicities, different molecular abundances, different radiation footprints. Some may contain ices that never formed within the solar system, shaped instead by the ultraviolet fields of distant star-forming regions, or the cooling gradients of far-off protoplanetary disks. The narrator imagines the quiet contrast a grain of ice that formed under a different star drifts past a comet that formed under ours, the two separated by billions of years of motion and trillions of kilometers of space sharing only this moment in the halo. Only took one galactic crossing to bring two ancient chemistries side by side. Yet a quiet scientific uncertainty remains how many interstellar objects pass through the Oort Cloud. Some models suggest the number could be enormous, perhaps millions present at any given moment, most too faint to detect. Others argue for a smaller population, noting that ejection of material from young planetary systems may be less efficient than once assumed. Without direct observation of the outer cloud, the true number remains unknown. Only took the limits of distance to keep the cloud's foreign guests uncounted. As the narrator drifts deeper, another subtle irony emerges. The Oort Cloud likely contains not only temporary interstellar visitors, but also permanent interstellar captives, objects captured by the Sun's gravity billions of years ago during its early life in a densely packed stellar cluster. If the Sun once drifted near other forming stars, its gravity could have pulled in material from their protoplanetary disks, mixing foreign fragments into the emerging cloud. These captured bodies would be indistinguishable from native fragments without detailed chemical analysis. Only took the Sun's youthful closeness to other stars to seed its distant halo with alien relics. A modern analogy enters the narration softly. The Oort Cloud resembles a quiet harbour at night, where drifting boats from unknown shores occasionally glide through, unlit, unannounced, leaving no ripple in the water and departing without anyone knowing they were ever there. The scale is incomprehensibly larger, but the feeling is the same shared space without shared origin. The narrator glides past another imagined interstellar visitor, smaller and darker than the first. Its orbit is inclined at a steep angle relative to the solar system's distant bodies, signaling its foreign origin. Its surface shows irregular structures sculpted by conditions different from those found in our system. Some of its ice sublimates at temperatures much lower than typical cometary compounds, hinting at a distinct chemical heritage. Only took a different star's warmth to create ices that behave differently under our Sun. The narrator reflects on how such objects might contribute to the broader understanding of planetary formation. Interstellar visitors carry information about the diversity of planetary systems throughout the galaxy. Their compositions reveal details about distant stellar nurseries, elemental abundances and early chemistry far removed from the Sun's environment. Yet their brief passages offer only the faintest clues. The deep compositional insights remain locked beneath surfaces unobserved and unstudied. Only took our observational limitations to leave the galaxy's diversity largely uncharted. A scientific detail deepens the atmosphere. Numerical simulations suggest that the Oort Cloud may exchange objects with other clouds surrounding neighbouring stars. When two stars pass within a few tenths of a light year, an event that happens occasionally across the billions of years of galactic motion, their outermost cometary bodies can be tugged away and transferred. These exchanges are rare but possible. Over cosmic timescales, they contribute to a quiet material mingling among stellar systems. Only took slow galactic drifting to turn the Oort Cloud into a crossroads of ancient fragments. Yet another uncertainty lingers: how significant is this exchange? Some models argue it may account for only a tiny fraction of Oort Cloud material. Others propose that during the Sun's early cluster phase, when neighbouring stars were far closer, the amount of captured or transferred material may have been substantial. Without direct exploration of the cloud, the true mix of origins remains hidden. Only took star cluster crowding to blend distant histories into the cloud's composition. The narrator drifts farther, sensing how serene this region remains despite the quiet exchange of matter. No collisions, no interactions, no visible evidence marks the passage of interstellar strangers. Everything unfolds too slowly, too gently, too sparsely to produce disturbance. Even when foreign fragments pass through, they do so in silence, leaving the cloud's native bodies unchanged. The only record of their passage is the subtle alteration of the Sun's gravitational field, an effect too small to perceive. Only took the universe's vastness to ensure that encounters between fragments occur without ever touching. In this immense stillness, the Oort Cloud reveals itself not merely as the solar system's outermost structure, but as a permeable boundary between star systems. It is a region shaped not only by the Sun's history, but by the galaxy's slow, patient drift. Interstellar visitors trace paths that cross the cloud's silent expanse, their brief journeys adding a faint richness to the frozen archive. Only took billions of years of galactic wandering to turn the Oort Cloud into a place where stories from many suns briefly intersect. And so, as the narrator moves onward, the presence of these interstellar travellers settles like a quiet acknowledgement of the galaxy's deeper interconnectedness. The journey continues through this subtle mingling of origins toward regions where the very idea of orbit becomes an arithmetic, too slow to grasp, shaped by distances so immense that even time feels stretched thin. The narration drifts farther still into the vast halo where the distances between frozen bodies grow so immense that any nearby motion feels like an abstraction. Here, the guiding sensation becomes one of immersion in a kind of cosmic mathematics, a quiet arithmetic of orbits. The narrator moves through a region where trajectories unfold so slowly that even the concept of a year dissolves. These are orbits measured not in the familiar cycles of planets or moons, but in spans that stretch into millions of years, where completing even a single loop around the Sun requires a patience that no living world could observe directly. Only took the universe's longest clockwork to give motion a meaning that borders on stillness. The scientific fact grounding this region is clear objects in the Oort Cloud have orbital periods ranging from hundreds of thousands to tens of millions of years. Their velocities are tiny, often just a few tens of meters per second, and their paths extend to distances where the Sun is only a faint gravitational anchor. Even bound objects creep along these orbits with such languor that entire geological eras on Earth pass before they advance a measurable fraction of their path. Only took the faint pull of distant gravity to define loops wider than any imagination. The narrator glides toward one imagined comet, tracing its vast orbit. From any point along its path, the orbital curve seems indistinguishable from a straight line because the curvature is too subtle to feel. It would take tens of thousands of years to see even a slight bend, hundreds of thousands to notice a perceptible arc. In a human lifetime, its position changes less than the width of a fingernail on a globe the size of the solar system. Only took a single orbit longer than the rise and fall of species to reveal motion where none seems present. A poetic detail emerges in imagining these orbits as faint chalk lines drawn in the dark, so thin and so wide that they vanish at any scale except the galactic. Some orbits tilt steeply, relative to the ecliptic. Others lie nearly perpendicular, and still others are retrograde, looping backward through the Sun's quiet gravitational reach. Their diversity reflects the chaotic scattering that sent them here in the first place. No two paths are quite alike, each is its own frozen equation. Yet a quiet scientific uncertainty persists. The true distribution of these orbital shapes remains unknown. Because astronomers detect long-period comets only when they descend into the inner solar system, the sample is biased toward objects already perturbed from their original orbits. The vast majority never approach far enough to be seen, leaving the deeper architecture of the cloud's orbital patterns hidden. Only took the remoteness of this sphere to keep its arithmetic partly unreadable. As the narrator drifts onward, another gentle irony becomes apparent. Though these orbits are unimaginably slow, they remain perfectly precise. Each comet obeys the same physical laws that govern the planets, even if its motion unfolds across spans that turn centuries into milliseconds. The same equations that describe the Moon's orbit around Earth also describe the slow loop of a distant Oort Cloud object. Only the scales differ. The arithmetic is the same, stretched across eons. Only took Newton's ancient insights to predict the dance of fragments that no one will ever watch complete a full turn. The narrator moves past two distant objects lying tens of millions of kilometers apart, but moving along paths that align almost imperceptibly when viewed from this vantage. Their motions resonate not with each other, but with the sun's slow journey through the galaxy and the faint breathing of the Milky Way's gravitational tide. Their orbital energies reflect the sun's tug, the galaxy's stretch, and the faint influence of ancient stellar flybys. In this region, every motion is a sum of forces gathered over deep time. Only took billions of years of accumulated nudges to write a trajectory that looks like near-perfect stillness. A scientific detail deepens this image. Many Oort Cloud bodies follow orbits that were once far more chaotic. During the early formation of the solar system, gravitational interactions with Jupiter and Saturn scattered icy planetesimals outward. Those that were not ejected entirely into interstellar space settled into elongated, loosely bound orbits. Over millions of years, the galactic tide adjusted their aphelia, smoothing their paths until they became the vast loop seen today. Their orbits now appear serene, but beneath that calm lies a history of violent beginnings. Only took the transformation of chaos into order to create the quiet geometry of the distant cloud. The narrator pauses near one body that spins slowly on an axis misaligned with its orbital plane. Its rotation is irregular, wobbling slightly due to small asymmetries in its shape. In a region devoid of friction, this wobble will continue for billions of years, preserved like a numerical error that no equation will ever fully erase. Its orbit, too, will continue to drift slightly as faint gravitational influences alter its parameters, changing its perihelion by fractions of fractions over each galactic cycle. Only took the absence of friction to let imperfections become permanent. A modern analogy arises softly. These orbits resemble the slow drift of buoys in a vast calm sea, each tethered by a rope so long the anchor lies beyond sight. The buoys move not with the waves, but with deep tides that rise and fall over distances too vast to perceive. The galaxy is that ocean, the sun its drifting anchor, the comets its patient buoys. Their motion is real, but it feels like rest. Yet even here, amid the slow arithmetic, questions linger. Scientists still debate how many of these long, slow orbits remain stable over the entire age of the solar system. Some models suggest that many Oort Cloud objects will eventually drift away due to galactic influences or passing stars. Others propose that new objects are continually added from the scattered disk via interactions with Neptune. Still others suggest that interstellar capture contributes to the cloud's population. Only took the complexity of cosmic influences to make orbital longevity an unsolved puzzle. The narrator continues gliding, sensing that each object's orbit represents a frozen story, its beginning dictated by ancient scattering, its middle shaped by tides and stars, its end unknown. Some will remain in the cloud until the sun dies. Others will fall inward as long-period comets, shedding their ancient material in spectacular displays near the sun. Still others will be lost to interstellar space, becoming wanderers between stars. Only took one shift in gravitational balance to decide a comet's entire future. Farther into the quiet, another poetic image arises. The orbits here form a hollow sphere of possibility, a silent architecture with no walls, but with patterns embedded in the distribution of paths. The narrator drifts through this orbital tapestry, slow, gentle, sprawling, aware that even the emptiness is part of the structure. Because the orbits are so vast, most of the cloud is empty space, yet that emptiness is shaped by the gravitational rules governing the bodies within it. Only took the geometry of gravity to sculpt a hollow realm where fragments rarely meet. As the narrator moves away from this imagined body, the arithmetic of the orbit settles into a kind of ambient knowledge, a reminder that the solar system extends not merely in distance, but in time. The Oort Cloud is a monument to orbital patience, a message written in trajectories so long that no observer will ever see them completed. Only took billions of years for motion itself to become a form of stillness. And so, the narration continues its slow drift, moving through this vast orbital architecture toward regions where darkness grows deeper still, where the absence of light shapes the outermost surfaces of these ancient bodies, and where the cold itself becomes a sculptor with immeasurable patience. The narration drifts farther outward into a realm where even the faintest traces of solar warmth surrender completely to the vast cold of interstellar space. Here the darkness feels thick, as though it has accumulated across billions of years without interruption, settling over everything like a soft, unbroken veil. In this region, the guiding sensation becomes the darkness that protects a quiet truth, that the lack of light, heat and activity is precisely what allows the Oort Cloud's ancient bodies to endure unchanged across cosmic time. Only took the universe's deepest shadow to preserve relics older than planets. The scientific fact grounding this region is clear at distances of tens of thousands of astronomical units. Sunlight is reduced to little more than a faint point. Its intensity drops to a level so low that surfaces remain only a few degrees above absolute zero. At such temperatures, chemical reactions slow to near stillness. Cosmic rays and interstellar radiation become the primary sculptors of surfaces, altering molecules, grain by grain, over spans so long that even a billion years feels like the rhythm of a slow heartbeat. Only took the absence of heat to give ice the durability of stone. The narrator drifts toward one imagined body, an ancient comet whose surface is a deep matte black shaped not by sunlight or warmth, but by radiation from the cosmos. Cosmic rays strike its surface continuously, their impact so subtle that each one changes only a few molecules. Yet over millions of years, these small alterations accumulate, turning clear ices into dark organic residues. The outermost centimetres become chemical palimpsests, overwritten slowly by the soft drizzle of high-energy particles. Only took a quiet cosmic rain to paint a surface darker than night. A poetic detail emerges in the way the comet's surface glows very faintly in the infrared. Though invisible to human eyes, every object above absolute zero emits a whisper of thermal radiation. Here in this profound cold, that whisper is so faint that it blends seamlessly into the background. Still, it exists proof that even in the deepest shadow, nothing is completely motionless. The narrator imagines this faint glow as a hushed warmth, a last trace of the sun's influence carried across impossible distances. Only took the faintest warmth to remind the dark that it is not absolute. Yet amid this long quiet, a scientific uncertainty remains. Scientists do not fully understand how cosmic rays shape the chemistry of Oort Cloud objects. While laboratory experiments can simulate some aspects of radiation processing the true environments of these distant surfaces, the exact particle fluxes, the exposure durations, the depth of chemical alterations remain beyond direct measurement. Some models suggest that radiation produces increasingly complex organic molecules over time. Others propose that surfaces eventually carbonize into simple residues. Which outcome dominates remains unknown. Only took our distance from these relics to keep their surface history half hidden. As the narrator glides along the object's exterior, faint lines appear, microscopic fractures caused not by heating, but by cooling. Even near absolute zero, materials expand and contract with tiny temperature variations caused by distant sunlight, cosmic rays, or the body's own rotation. These minute changes generate stress over millions of cycles, cracking the outer crust into delicate patterns. On Earth, Such cracks would be ephemeral, erased by weathering. Here they persist indefinitely. Only took imperceptible temperature shifts to write intricate patterns that no warm world could preserve. The deeper into the halo the narrator drifts, the more pronounced the darkness becomes, not because there is less matter, but because there is less light to reveal it. Some bodies reflect so little sunlight that telescopes would see them only as the faintest glimmers, if at all. They drift like shadows cast by no source, invisible against the deeper background. Only took a few million years of surface darkening to hide these relics from every eye. A subtle irony settles the best preserved materials in the solar system reside in the region least accessible to observation. While planets, moons, and asteroids have been reshaped countless times, these far bodies remain almost perfectly unchanged. Their remoteness and darkness protect them from everything heat, weather, impacts, erosion, even from the curiosity of young civilizations eager to understand their origins. Only took cosmic inaccessibility to preserve perfect archives. A scientific detail deepens this image. Cosmic rays penetrate only the outer layers of these bodies, barely reaching depths of a meter or two. Beneath that thin shell lies ice unchanged since the early solar nebula. This boundary between altered surface and pristine interior creates a chemical gradient that tells a layered story, the outermost few centimeters. Record radiation, processing. The next layers preserve early solar system chemistry. And deeper still lie materials inherited from the molecular cloud that predated the Sun. Each depth is a different era, a vertical timeline frozen in place. Only took billions of years of stillness to stratify history so delicately. Yet uncertainty lingers here as well. Scientists still debate the exact composition of deep cometary interiors. Some models suggest that amorphous ice dominates. Others argue for crystalline structures shaped by early heating events. The presence of trapped gases, complex organics, and pre-solar grains also remains uncertain without direct sampling. Missions like Stardust and Rosetta illuminated part of the picture, but left the deepest layers unexplored. Only took technological limits to leave core chemistry an unresolved question. The narrator glides past another imagined fragment, noticing how its surface seems slightly smoother than others. This smoothness may result from micrometeorite bombardment, tiny dust grains striking the surface over billions of years. Each impact, though minuscule, erodes the topmost molecules, smoothing edges, rounding fractures, and producing a fine regolith of particle fragments. In the absence of atmosphere or geological activity, this slow erosion becomes the only sculpting force. Only took a drizzle of microscopic impacts to turn rugged surfaces softly worn. Yet even these dust grains originate from ancient events, long ago collisions between distant objects, fragments from early solar system chaos or dust drifting through the galaxy from other stellar systems. The comet's surface holds the signatures of impacts from across cosmic history, a landscape sculpted not by winds or water, but by the steady accumulation of nearly invisible touches. Only took a universe of small encounters to craft textures older than Earth's continents. As the narrator moves farther outward, the darkness stabilizes into an almost tangible presence. It is a protective cloak, a barrier against transformation, a quiet assertion that distance and cold preserve what time alone would erode. In this region, the cold does not simply slow processes, it stops them. The darkness does not conceal, it protects. And in that protection lies the deepest continuity of the solar system's origins, a quiet preservation of states so ancient they predate every mountain, every ocean, every cell that has ever lived on Earth. Only took cosmic stillness to guard the oldest stories, and so the narration drifts onward through this frozen hush, preparing to move into the realm where even this fragile preservation begins to dissolve, not because of destruction, but because the Oort Cloud itself eventually yields to the greater darkness beyond its boundaries, fading into a region where the sun's influence becomes indistinguishable from the interstellar night. The narration drifts into the farthest reaches of the Oort Cloud, moving toward regions where distance outgrows even metaphor, and the sun's influence grows so faint it becomes almost a memory of gravity rather than the thing itself. Here, the guiding sensation becomes the edge that never ends, not because the solar system possesses a firm boundary, but because its influence fades so gradually that no precise line marks where ours becomes not ours. Instead, this distant frontier is a dissolving gradient, a slow fading of belonging into the vast anonymity of interstellar space. Only took the universe's patient expansion to turn distance into a kind of silence. The scientific fact grounding this region is simple yet profound. The sun's gravitational domain, known as its Hill sphere, extends roughly 1 to 2 light years in every direction, depending on the density of surrounding stars and the sun's position in the Milky Way. But the Oort Cloud, though often described as a sphere, does not fill this entire volume. Instead, it fades outward, its density dropping continuously until it becomes indistinguishable from the background dust and interstellar debris drifting between stars. Only took the galaxy's slow currents to blur the solar system into the larger cosmic sea. As the narrator drifts deeper into this far frontier, the scenery simplifies. The cometary bodies that once seemed rare now vanish into separations measured in tens of billions of kilometers. A single fragment may drift alone for millennia, without passing within sight of another. The emptiness expands beyond intuition. Here, isolation becomes the defining state. And yet the narrator senses a subtle paradox. This emptiness is still part of the solar system, caught within the sun's distant gravitational persuasion, even if that persuasion is less a force and more a lingering suggestion. Only took the faintest echo of gravity to hold distant relics in a realm more empty than any desert. A poetic detail emerges in the way the sun appears from this frontier. It no longer resembles a star with planets. It is merely one faint point among many indistinguishable from the countless stars drifting through the Milky Way. Only those who carry the deep memory of its warmth, worlds like Earth and Mars, could ever identify the sun by more than brightness alone. Out here it loses that identity, entirely settling into anonymity. Only took a drift of 500 billion kilometers to turn the sun into just another light in the dark. Yet even in this extreme quiet, a scientific uncertainty persists. Astronomers do not know exactly where the Oort Cloud ends. Simulations suggest it may stretch halfway to the nearest star, Proxima Centauri, but its outer boundary is defined not by distance, but by competition. Where the gravitational pull of passing stars becomes comparable to that of the sun, the cloud's outermost members drift freely between dominions. Some may be captured by neighbouring systems, others may be lost entirely. Only took the galaxy's crowded neighbourhoods to make ownership of comets a temporary agreement. As the narrator glides into this threshold, the region feels less like a structure and more like a transition, a zone where influences mingle and identities blur. Comets here orbit the sun so loosely that a single stellar passage could redirect them. Over billions of years, such passages have shaped the cloud into its present diffuse architecture. Some stars, like Schultz's star 200,000 years ago, pass close enough to stir the cloud's outermost members, sending some drifting inward, and others outward toward interstellar release. Only took a wandering red dwarf to rearrange the fates of ancient fragments. The narrator imagines one such comet on the brink of escape. Its orbit is elongated nearly to the point of departure, with its aphelion so distant that the sun's gravity barely restrains it. It drifts along this trajectory slowly, silently each year, nearly indistinguishable from the next. But beyond a certain point, a point without a line, the gravity of another star, or the faint gradient of the galactic tide may tip the balance. And when that happens, the comet will leave the solar system, forever entering the vast expanse between stars as an interstellar wanderer. Only took a slight imbalance in the universe's arithmetic to set a relic free. A poetic irony settles quietly. The Oort Cloud's inhabitants, bound for billions of years, may eventually spend longer wandering the galaxy than they ever spent within the sun's domain. A comet formed around the newborn sun might drift for 10 or 20 billion years among the stars after the sun has faded, carrying within it the frozen record of our system long after its planets have vanished. Only took cosmic patience to let relics outlive their maker. A scientific detail deepens this image. When stars pass nearby, they can also add material to the cloud. The sun may capture foreign comets, adding them to its diffuse halo. Over time, the Oort Cloud becomes a blend of native fragments and interstellar guests. Its outer boundaries are shared not only with the galaxy, but with the histories of other stellar systems. In this way, it becomes a bridge between stars, a quiet archive of many origins. Only took silent exchanges across light years to turn the cloud into a mosaic of cosmic pasts. As the narrator moves farther outward, even this faint structure dissolves. The gravitational influence of the sun wanes until it becomes mathematically negligible. The dark becomes deeper still, and the emptiness approaches the true interstellar medium, a sparse collection of atoms and dust grains drifting through the galaxy. Here, a few stray particles per cubic centimetre define the environment. These particles pay no allegiance to any star. They drift freely, shaped only by the galaxy's general gravity, and by the faint currents of interstellar winds. This is where the Oort Cloud ends, not with a boundary, but with the disappearance of pattern. Only took the galaxy's immense quiet to erase the final traces of structure. The narrator lingers on this dissolving frontier. It is not an edge, it is a fading. No distinct markers, no changes in scenery, no sudden shift from belonging to not belonging. Just the slow weakening of gravitational influence until it becomes too small to matter. In that slow fading lies a profound calm. The solar system ends not with a boundary, but with a whisper. Only took the universe's gentlest gradient to define the farthest reaches of home. As the narration pauses at this conceptual doorway to interstellar space, the Oort Cloud's role becomes clear. It is the softest, quietest, most ancient halo encircling the sun, a place where time drifts freely, where shadows guard memory, where borders dissolve into silence. And beyond this threshold lies something even quieter, the interstellar dark stretching between stars like an endless sea, that knows no centre, no edge, no origin. Only took a few trillion kilometres to reveal how the familiar becomes indistinguishable from the infinite. And so, with the faint light of the sun barely visible behind the narrator's slow outward drift, prepares to dissolve into the wind down where motion ceases and time itself feels suspended, resting gently in the dark between stars. The narration drifts into a realm beyond motion, where even imagination begins to slow, where the ideas of distance and direction soften until they feel like traces of thought rather than places in space. The outermost edge of the Oort Cloud fades behind, not as a line, but as a dimming memory, and what remains is a sense of drifting without purpose, without boundary, without anything urging the mind to move forward. Here, stillness takes on its fullest shape. The dark is not an emptiness to be crossed, but a quiet in which the mind can rest. The sun is now only one among many distant lights, a faint mark on a canvas of slow stars, and even that mark feels optional, something the narrator might turn away from without losing orientation. All that remains is the calm of space itself, the soft hush that lies between every gravitational pull and every flicker of radiation. In this wide, quiet region, the motions that once shaped the solar system fall away. The long arcs of comets, the slow tides of the galaxy, the faint exchange of matter across the cold halo, none of it presses forward now. All narratives lose momentum here, as though the universe has paused its vast arithmetic for a moment. The drift becomes gentle enough that it feels like settling, like evening shadows smoothing across a landscape, like the last light dissolving from a distant horizon. There is no past and no future in this space, only a soft present that spreads itself thinly across the dark. Only took the universe's oldest silence to remind the mind that nothing more is required. The cold carries no urgency, the darkness carries no weight. Each breath of the cosmos seems to come farther apart until even the concept of breathing becomes abstract, replaced by a sense of floating in a medium that does not press or pull. In the absence of temperature, texture, or light, the mind drifts freely unburdened by motion or memory. Thoughts loosen like dust in a still room. Patterns dissolve. The idea of the Oort Cloud becomes only the faintest echo of what came before, softened by distance and by the calm that settles naturally when nothing asks to be understood. This is a place where time does not push. It simply allows. The quiet grows thicker like a deep layer of snow that muffles every sound. Even the notion of observation fades. There is no need to follow a comet's path or consider a star's gravity. There is no need for the mind to hold on to structure. The universe does not require attention here, it invites release. In this slow quiet, the narrator drifts without destination. Space stretches outward indefinitely, but it no longer feels vast, it feels gentle, like a soft surface dissolving into itself. The stars seem less like points, and more like distant thoughts scattered softly and without brightness. The sun is only one thought among them, flickering faintly but without urgency. The drift continues until even drifting feels like too much. The story unspools into quiet threads, each one softer than the last, until nothing remains but the sense of resting in a space made entirely of calm. No movement, no sound, no need for direction, only the long patient quiet at the edge of everything. And in that silence, the narration comes to its natural rest, letting the universe hold the moment steady, letting the mind drift into stillness as gently as a comet moving through deep night.